Hello, guys. I hope everyone is doing great. So, today, the problem statement that we are going to tackle is we are going to design a system of a distributed message queue. Now, everybody who is in the software engineering platform, I think they have known through the terms like Kafka, RabbitMQ. In AWS, there are things like SQS. In Azure, there are things like Service Bus. So all these things are uh, either some kind of a variant of a message queue or a streaming platform. Now, the very first thing, as you see as a in the heading, that I am using this message queue or streaming platform, but I'll be very careful to say that message queue and streaming platform, these two things are not exactly same. So how they differ? Before going into the nitty-gritty of the system design of a distributed queuing service like Kafka, let's delve into the details of a message queue. But before that, like a little history about the Kafka. So Kafka is one of the great engineering example of the necessity is the mother of the invention. So Kafka uh, was created by LinkedIn when they faced like a major scaling challenge. To mitigate their major scaling challenge and how exactly they do it, we will probably try to take a few of the use cases of LinkedIn and why they had to come up with some kind of a queuing platform, and why it changed the face of many architecture around the industry that we will try to uh, that we will try to discuss throughout this video. So before going there, let's discuss about what exactly is the message queues, and then we will come to the details of the streaming platforms, and probably it will be easier for us to understand the requirements, and then we will go ahead with our key design decisions, the nitty gritty of the implementations, whatnot. Okay, so when we are talking about the message queues, the core purpose is there is a point to point messaging, and only once delivery. So suppose there is a system like this, and this system, what it will do is like this is my message queue, suppose. Okay, I'm just abbreviating as MQ. What this MQ will do is MQ will make sure that if there is some kind of a worker process, what that worker process does is it will just what that worker will do is it will just consume it only once. So when I say worker process, that means suppose you are receiving a SMS from a certain service provider, and often you will see that you are getting just duplicated SMS. So that kind of thing is not once per delivery. What happens is that system in some way couldn't guarantee the only once delivery which is necessary, but message queues, they guarantee you the only once delivery from the message queue to the worker. And how it is being done? It is being done via polling. So polling is a responsibility of the worker. So in case I am writing a suppose a simple console application or any kind of worker process, that worker process will keep on looking into the message queue that, hey, do you have something for me, do you have something for me, and from that queue it will keep on enqueuing one by one. So what are the primary things here? So as you can see, like only once delivery, that is a very important sorry, yeah, so only once delivery, that is a very important part of this. Then there comes like a temporary retention, and temporary retention is again a great point, given in this message queue, the message will not be stored for indefinitely. Suppose there will be some kind of a time to live, and suppose it is 7 days. So in 7 days, if you as a worker, you are down, like in system design, when we say like the outage sort of a thing, it is happening and it is unable to poll for a stipulated time, suppose for 7 days. then this message will be completely gone. It is not a persistent storage sort of a thing. So that is the very much very like a very basic difference between the database and a queue. Like who are just seeing this video as a base understanding of queuing for the first time, that is a very like that is a very basic difference between a queue and a database, that a message queue only hold the particular data for a temporary time. And what it has is plus there is one more feature it has, that is called competing consumer. So what does competing consumer means? Competing consumer means that suppose there are here we are working with one worker, and suppose there are like worker 1, worker 2, worker 1 and worker 2. Let's make it like this. Now suppose there is a certain message that is coming, certain message is there, suppose, and this message is to be delivered to worker 1 or worker 2. So both of them will keep on polling, and the thing is that whoever will get the message first, suppose worker 1 gets to poll it first, so it will be sitting with worker 1. In case worker 2 polls it first, it will be there in the worker 2. So it will not be available for the other worker. That is a very basic um, yeah. So that is a very basic feature of the message queues, that it will have competing consumer, and if one consumer at any point of time uh, at any point of time it gets a certain message, the other worker doesn't. So let's take some kind of a in industry use cases, and what are the popular message queues in the market right now. So in case you have heard about RabbitMQ, or there is like ActiveMQ, these are the message queuing services. And if you are one of the AWS junkie, you might heard about the AWS SQS, simple queuing service. So that is also a sort of a message queue. So let's take example. So when we take example, let's think of some kind of a e-commerce order processing. E-commerce orders, how they are being processed. So orders are, so suppose there is a order. What this order will be done is, this order will be, suppose again I have a queue, this order will be placed in a queue. Okay, so this order will be placed in this particular queue. I think I need to bring it front or something. Okay, so order will be in this queue, and from there what will happen is the worker services. So let's take this worker, suppose this worker services will keep on polling the order. Worker services will keep on polling this orders queue, and what it will do is, one at a time, it will keep on sending the data, for example for the payment processing, okay, or for the inventory check. And in this way exactly, s- one time this data will be, this order will be delivered to this worker. And as we were discussing, the worker probably have like separate responsibilities via some way, like inventory, payment, all this thing will be called from here. Okay, so this is how a order works. And one of the very like other popular example is our messaging service. So like when we say about SMS and emailing, it is always expected that we receive only we receive it only once. So suppose any bank transaction happens, so that bank transaction, so there are multiple things might be happening, but suppose I have some queue which is responsible for SMS and email. This bank transaction will be placed in this queue, and our worker process will make sure that it is being consumed only once per delivery because of the polling, that once delivery. And from there what will happen is it is expected that we are going to get the uh, one SMS of that transaction and one email. So in this way, this once delivery model is being exploited to make sure that only one delivery happens here. Now let's discuss around the other part of the things that we wrote here, that is the event streaming platform, and it is the most interesting thing, and this is something that we will try to design. So event streaming platform, let's discuss about it. So we will just see it with a visual example. So suppose I have this event stream. I have this event stream. Okay, I'll be careful not telling it queue because the previous thing was queue. But again, event stream, just for a sake of understanding, it is kind of a queue only. But why I am more keen on calling it as a queue? Let's discuss around that. So suppose I have this event stream. So all the dashes that you see over here, these are suppose separate elements or the messages. Like here one message is there. Suppose here also one more message is there. In this way, the messages are in all of these places, right? In the event stream. Now, what it works is it works as a persistent, ordered, and replayable. Now let's understand each point one by one. So when I say persistent, that means it event stream can persist data maybe for 7 days and even 1 year. Like there are cases, industry use cases where the event stream in that particular stream or in the queue is being sustained for maybe 6 months, 1 year for multiple cases. And then you just think that about the replayable means, for example, today there is a consumer, so instead of worker I will just shift my nomenclature a bit. I will now keep on calling them as consumers. Okay, so if a certain consumer, so these are the two consumers are there, so if a certain consumer today reads this data, suppose this data is being read by this guy. Okay, this data is being read by this guy. Now this particular element, although it is behind, but if consumer 2 wants, using a property called offset, he can he can just read from the event stream as a consumer any message in that particular stream or in the queue. Okay, so we call it replayable. And ordered means like when while inserting the data, whatever the order we are maintaining, if a certain consumer uh, keep on reading the data one by one, they will be consumed in that particular ordered fashion. So these are the basic uh, three features of like persistent, ordered, and replayable. And of course this model is this model is a variant of again queuing only, but we will we will call it a stream, and on this stream there are many other processing that we can do, like we can do filtering, we can do aggregation and whatnot, but we will come to those things later while we are implementing it. So now let's discuss few of the industry use cases of the event streaming platform. So before that, a few examples of very popular event streaming is Kafka, Pulsar, yeah, this sort of things. Now, um, the industry use case is yeah, a very popular industry use case will be real time user activity tracking. So just keep on thinking, like you have developed a social media application like Instagram or Facebook. So you want to understand where user keep on clicking into your social media application. So for that, the kind of application that we can do is like the click aggregation service, and this click aggregation service are nothing but the click aggregation only can happen once it passes through some kind of a string. So whatever the user clicks, it goes through either Kafka or any other kind of streaming platform, and from there the click aggregation happens. Okay, so a social media's click aggregation app which tracks the clicks, likes, or shares. Those events are being streamed into Kafka, analyzed for multiple things like recommendation, ads, or even fraud or forgery detection sort of a thing. And even multiple teams like the analytics team, the machine learning team, and the security team, they can consume this data. So if we take this event stream as an example of ad, like multiple ad clicks, instead of ad I would say like user clicks are coming there. User clicks are coming. So what will happen is, suppose there is a ML ops team which keep on checking that whether there is any suspicious activity or not. There is another ad service, or as I was talking about, the ad aggregator team, which try to understand the user behavior from there and try to find the ad aggregator and the recommendation engine. What it does is it creates the ad aggregator and the recommendation engine. And also of course, because this data are huge in volume and very fast, it can be processed. So even like iot iot sensor, for IoT sensor data capture, like Apache Pulsar in this is one of the widely used streaming platform across the industry. So what it does is, like, suppose you are running some kind of a cold storage factory, okay, so it have lot of things like a lot of rooms, lot of temperature, and how exactly how much weight those machines can carry in your cold storage. All those details can come up, like in a single second, how much temperature is changing. All those nitty gritties done uh, can be captured using Apache Pulsar, and then we can use it for various kind of analytics or machine learning and whatnot, and decision making. And like, now that we know both message queue and the event streaming, now let's see their convergence. Okay, so when I say convergence, I mean in recent times, if we see, okay, in recent times, if we start to see like how exactly these queues are being used, we will see that uh, Apache Kafka or RabbitMQ, okay, they can either be used as a message queue also. They can on the other side can be used as a event streaming platform also. Okay, so the modern tools, they are borrowing the like best of both queuing and streaming. So but still it is a very important concept while we are designing an application. So I thought of covering this in the first place. RabbitMQ or Apache Pulsar, again, if you just go into their documentation, you will be able to understand, or you can just use any LLM to understand how Kafka can be used as a queuing, how Apache Pulsar, although being a primarily a streaming platform, it can also be used for queuing. So now if we keep on talking another point of latency or the throughput, then we have to understand that this is very high throughput. Like our streaming platforms are very very high throughput, like probably millions per second is nothing for Kafka. Like as we were discussing that LinkedIn came up with the Kafka to support their own infrastructure, so that was their primary problem. Like when like millions of users are clicking into a post or interacting with a post from uh, different part of the globes, how exactly they handle that stream of events. So Kafka saved the day for them. But anyway, like all credits to them, because of them only a lot of things got changed in like in coming times when they did it. And also like one more thing is like ultra low latency. This has like sorry, this has low latency. This has a little low latency, like in uh, milliseconds probably, whereas the when I say latency, like how fast the data can travel within the queue, and whereas if we see our message queues, I'd say that it is ultra low. Like the moment the message comes, immediately it becomes available for consumption. In case any polling remains, then of course it remains in the queue, but yeah, it doesn't take any time to be available for consumption. So this latency and throughput, again, one of the two things you can uh, distinguish, but again, as the tech is progressing, both of them are converging, so it's completely fine at times. Like you can convert your queue architecture to a streaming one as per your wish. So now when to use what? If you have to see, like in case you have to guarantee only once only delivery, what you will do? Like suppose once only delivery is my requirement, so what I will choose? If your guess is queuing, right? So suppose I need a replayable data, so what will be my selection? Replayable means like at any point of time will be able to go to I probably will be able to go to that particular point in the queue. So that is something we will probably select our stream or Kafka. So stream and Kafka, we will keep on interchange. We will keep on using this word interchangeably. And yeah, now let's again talk about some very basic real world examples. So one would be Netflix. So in Netflix, what happens is they uses Kafka for real time monitoring and event driven microservices. uh, uber Uber uses Apache Pulsar for the driver dispatch. In case like you don't know how Uber does this driver dispatch, you can just go and do some YouTube search. Like many content creator, they have explained how the Uber dispatch service works, and how the search prices also work. So for that, they uses Pulsar and LinkedIn. Again. No streaming discussion will be completed without LinkedIn. So they built Kafka to handle their activity tracking and the matrices. And very interestingly, Tesla, like in their car, they have some kind of a telemetry task distribution. So the whole telemetry in the Tesla cars are being done by RabbitMQ. So now These are the very basic things of uh, streaming and the SQS differences. Now, in addition to that, because this video will anyway be longer, I understood. So I also want to uh, tell one of the very basic understanding around SQS, that is AWS SQS and Kafka, because both of them are like immensely popular. So how exactly the message retention is being taken care in both of the system, that is a very interesting thing. So suppose we are talking about SQS. So SQS has a certain queue, and in this queue, suppose there are like 1 2 3 4, like multiple messages are there. Yeah, so all these messages are being traveling into the queue. Now when this message is being processed by the worker, suppose I have a worker over here, and this worker in some way, it process this message. Okay, the moment this processing is being done, unless, this is important point, unless explicitly deleted, this will reappear, this message will reappear in queue after visibility timeout. So excuse my spelling. So this, unless explicitly deleted, this message will reappear in queue after that visibility timeout, right? Now what generally a consumer should be doing is, a consumer should, like, the moment it consumes the message, it should delete it. So this is how visibility timeout works, and this is one of the very important point on the message retention. So, and but message will be automatically deleted also, like this is also a point, it is automatically deleted after a certain TTL. Okay, so after 14 days, even if you don't delete it as a consumer, you don't, like, it will anyway not be appearing. For example, here as we saw, this particular message, if it is not deleted, it will again appear in the queue somewhere here, or like in just in this process after that visibility timeout. But once it passes this TTL, it will not. Okay, now in Kafka, how the data retention happens. So in Kafka, the data will be by default written for the 7 days. So again, if I can draw this queue for Kafka, so suppose there are like messages like this. Okay, now this will stay there for stipulated time, like 7 days. Okay, this is of course configurable. There is the log.retention.hours one property is there in our Kafka config that we can do, and also like there is a size based retention as well. Like if your queue size is going beyond the uh, going beyond the size, then also we can uh, probably delete it. So uh, yeah, this is what the replayability is again, and as the message retention, you can understand the differences of visibility timeout and replayability within a whole queue. Now the question is, like, all this theory and everything, what exactly we will build? So we will build something called as I have discussed at the top of this, we will build Kafka, and we will have features like long data retention, configurable of course, and repeated consumption. Like if one consumer is consuming, it should be available for the other consumer as well. And also like and also in this process, we will just see how we can scale this thing across the globe, how Kafka works closely with something called Zookeeper, and we will again anyway discuss with all these things. Okay, discuss all these things in detail where I will come. But before that, uh, like also we should understand one more thing called the pub sub model. So other than queuing, I will be real quick with the pub sub model, because if we don't cover pub sub model, it will be sort of an injustice to all the learning that we are having here. So pub sub model, what it does is, suppose there is simple notification services in AWS. They have like AWS have it is as a one of the very popular tools. So what it does is, the moment it reaches into the in case I just use this queue only, the moment it comes into the queue, suppose I have like 10 worker processes. Okay, so worker 1, in this way I have like worker 2, worker 3, something like this. So what will happen is, it will be notified to all of them, like to this, to sorry, to this, to this one, everywhere it will be notified. And suppose this is suppose w2, this is suppose w3, and this is suppose w4. What will happen is, if these two are down by any means, suppose these two are not available, then message will not reach there. There is no visibility timeout, no retention, nothing. It will be pub sub. It will be just published to the available subscriber at that point of time. And the example is AWS SNS. Okay. So for HTTPS endpoint, in this process, I should mention that HTTPS endpoint, SNS tries to deliver few times with a certain exponential backoff, but for other things like email and SMS, there are no retries at all. So as we are going to design our own Kafka, so in in our Kafka we had sorry. Okay, so in our Kafka we have written all these things, right? So what? Okay, let's. I don't know. Like I cut it and I don't find it in my clipboard. So this Kafka, what we will have is like it will hold mostly a text-based messages. Like you cannot really send an image or video in a queue. Okay, that will be too much of a ask to application. And repeated consumption. Then there will be like retention of 2 weeks, something around that, and very high throughput, like millions per second, something like that, like for ad aggregation, suppose. Now let's start with a very high level thing. So there is a producer. So before this queue, there will be a producer. So suppose I write it as a P. Okay. So this is our queue, and what we want to do is we want to have one, two, three, four, all this different, like these are consumers. Okay. Okay. So these are consumers, and these are, and this I will mark it in black. This black one is a producer and they are consumer. So very high level, what will happen is, from producer data will go there, and from consumer data will go here, from queue, sorry, not from consumer, From queue, the data will go into this. Yeah. Now, so for messages platform, what are the basic things over here? Now let's understand a little bit of theory around this. So we learned about this queue, right? So how this queue will be able to send the data to so many consumers, or at least make it available for so many consumers. So for that there are some popular terms are there, and how exactly this queue is designed. So queue, we have something within every queue that is called topic. Okay, that is called topic. So what exactly topic is? Say LinkedIn uses a single queue for all activities. Okay, suppose for posts, messages, notifications, like profile updates that you completed this many years in your organization. For all these things, suppose what will happen, suppose user A is posting something, and by the time he realized that that post is not correct. Okay, and by the time user B has already commented something on that, maybe within fraction of seconds, and users A's deletion request is still waiting in the queue. So in case we do not segregate all these things separately, what might happen is, suppose there are lot many notifications are going on, users posts might be waiting indefinitely in the queue. Like placing all of this thing in a single queue will be too much, like system won't be able to handle it. So what the so what kind of design at that point of time LinkedIn came up with this while developing Kafka, that they will have topic. So each topic, so this above are each topic in LinkedIn Kafka, in LinkedIn Kafka streaming. Okay. So topics are basically like logical categories or like folders, you can see, and from that folders our different consumers will keep on pulling their data. For example, for posts there will be a certain kind of consumers or consumer group also, we can say. We will come to that in a later point of time. Now, as we were discussing, like how messy it would be, like for LinkedIn the user posts, then the direct messages, notification, profile updates, if all they come into a single one. Okay, now uh, there is alongside topic. So suppose within this we have this as a topic. Okay, so alongside topic there is also something called partition. So what partitions are? Partitions are division within the topic. So it is like parallel pipelines within a topic. Suppose a user, like there is a consumer of posts. Okay, so whatever the user posts, it goes through it post. You just think in terms of scale. Okay, how difficult it would be to design, like this particular system. Okay, how difficult it would be, like this particular system is getting probably 10 million requests per second because everybody is posting like across the globe. So how difficult to maintain this particular consumer and this queue will be. So for that reason we generally have different sort of segregation. So suppose only for posts done by user A to M. Okay, I'm going to handle by one consumer, and what will happen is this user A to M will come in a certain partition, and that partition in turn will have a given consumer. So that is why uh, the partitions are necessary, and within partitions, of course, that is the lowest unit, I would say. There will be one queue, and there is a like uh, there can be consumer groups, like multiple people might be consuming, but as a group they will be consuming it. Okay, so why these consumer groups are important again? So now what we learned? We learned topics, we learned partitions, and now we are talking about the consumer groups. Yeah. So consumer groups, let's say, let's take an example like Uber. It uses individual consumers to process messages like ride requests, uh, driver location update, the search price calculation. Now, in Uber, what might happen is, suppose 1,000 requests are there. Okay, suppose 1,000 requests are there and it hit a certain topic, and we have 100 consumer without grouping. So all the 100 consumer, it might try to read the same message, which I do not want. What I want is that the driver, the ride request will be read by a certain line of the consumer. The driver location updates will be read by a certain consumer, and the price calculators, so they will be again they will be again consumed by a certain consumer. Now consumer groups, you can think it like a teamwork. Okay, so as a team they are performing a certain duty. So in Uber, what will happen is, the moment this ride request comes, we are going to split it into a partitions as a different geography zone, and probably even as a bigger city. For example, if you are in Bangalore, that should be a different partitions, and if you are serving your customers in Hyderabad, that can be a different partitions. And what we can have is, like, there can be 10 consumer for that ride request and in that Bangalore location, and there can be 10 consumer of that ride request in the Hyderabad location, and all these 10 consumer process all the partitions. So this 10 10 consumers are like, will always be pointed to that particular partitions that they are serving. Okay, now um, there is a critical constraint. So one consumer or one consumer uh, are there per partition or per group. If two consumers of the same group read from the uh, same partition, okay, that will be breaking the order. So again, I will write it for you. If two consumers in a same group read from same partition, then it will break the order, it will break the order guarantee. Okay, so that is and also like there are there there is also a possibility of um, what I could say, the same, they can assign the same driver to a different request. That kind of thing might happen there. And a partition can only be consumed by only one consumer per group. So a partition 3 is there. Suppose for the airport rides there is a certain partitions, and there is a consumer 5 which will only read from that partition 3, and if consumer 5 crashes, the group probably will rebalance. There is this active or the active passive thing will come in play. Now this this was the very basic theory, I would say. before we start actually implementing. So this is the first part of this video for the message queuing and the message streaming, and we'll be back in the next part where we will talk about the scale, we will talk about the actual design deep dive and the actual scaling. So this was again a foundational thing to and what will be the basic takeaway from this is difference between the queuing services and the streaming services, and when we are doing queuing, what are the guarantees, at the time of streaming what are the guarantees, also like what are the topic, what are the partitions, what are the consumer, what are the consumer groups for a streaming. If we get those ideas, then I think we have a pretty solid ground to proceed with our actual design discussion. Thank you so much. If you have any question on this, please post in the comments. I will try my level best to answer this. And also, the second part will be there soon, probably within the couple of days. Till then, all the best, and thank you very much.